Every time you swipe your card, click a link, or buy something online, you're interacting with a database. But honestly, have you ever stopped to wonder how this massive, relentless flood of global data doesn't just collapse into total chaos? Well, in this explainer, we're demystifying the hidden engine powering our digital world, the relational database.
Let's map out our journey today. We'll start with the evolution of data. Enter the relational model, unlock the power of keys, speak a little SQL, tackle constraints and anomalies, and finally, weigh the great database balancing act.
Section 1. The evolution of data. To truly appreciate how smoothly we manage information today, we really have to look back at the messy, fragile systems of the past. Before the 1960s, organizations basically dumped data into entirely disorganized flat files. It was a mess. Then, IBM introduced hierarchical databases, these really rigid tree-like structures. Fun fact here, this was the exact system that helped Apollo land on the moon. Pretty cool, right? But man, it was incredibly hard to modify. It wasn't until the 1970s that the relational model finally brought some true balance, paving the way for the modern NoSQL and cloud systems we use in the 2000s and beyond. The crucial takeaway here is why we had to evolve. Those early flat file systems were plagued by high redundancy and severe inconsistency. Imagine updating a customer's address in one file, but just completely forgetting to update it in 3 others. Your data was duplicated and incredibly vulnerable. Computer scientists literally had to rethink the whole shebang.
Section 2. Enter the relational model. So, in the 1970s, an IBM mathematician named Edgar F. Codd stepped in and completely revolutionized the field. He did this by applying pure mathematical set theory to organizing data, a real game changer.
Let's demystify some of the jargon, starting with the tuple. Now, while we commonly just call this a row, Codd used the term to enforce mathematical rigor. It represents one distinct, unduplicatable entity, like a specific student's record, within a strict set. It's not just a line on a page, it is a discrete mathematical object.
Next up is the attribute, which is simply a column. If the tuple is the student, the attributes are the exact properties describing them, their name, their phone number, their major. This concept ensures every single data point remains atomic and perfectly structured.
And finally, we have the schema. Now, this isn't just a basic layout, it's a strict structural blueprint. Think of it as the absolute contract that tells the database exactly what to expect before a single byte of data is ever written into the system.
Section 3. The power of keys. So having perfectly structured, isolated tables is honestly pretty useless unless we can actually map the relationships between them to build a larger picture, right?
That's where the foreign key comes in. This acts as a secure structural bridge. It's basically an attribute in one relation that is strictly, firmly bound to the primary key of another.
Let's look at how this works. If you have a results table with student IDs 1 and 2, those act as foreign keys. They are tethered directly back to, say, John and Mary in a primary students table. There's no redundant typing going on here, just a seamless, unbreakable bridge between the data.
0. That is the exact number of duplicate rows or blank, null values allowed in a primary key. It guarantees absolute uniqueness. If you try to force a duplicate into the system, no way, it'll be flat out rejected.
Moving on to Section 4, Speaking the Language, SQL. With our architecture locked in tight, we need a way to actually command the system.
This brings us to Structured Query Language, or SQL. And SQL is surprisingly English-like. It uses 5 foundational operations to give us total command over our data. You create tables, insert data, select exactly what you want to see, update things when they change, and delete when you're completely done with a record.
For instance, if we execute an update command targeting student ID 1, a record for John instantly becomes Peter. It's precise, logical, and executes across the entire system in a fraction of a millisecond.
But hold on, before a single line of SQL is ever written, there is a strict 4-step design process. You don't just sit down and start coding. First, you have requirement analysis, then conceptual design to map out your entities. Third is logical design to plan the tables, and finally, physical design. This whole process ensures the database is fundamentally sound from day one.
Section 5, Constraints and Anomalies. Because let's face it, even with a flawless design, data inherently drifts toward entropy over time. Without rules, we invite anomalies. These are really dangerous irregularities that happen during insert, update or delete operations. Imagine trying to delete a single department from a college system and accidentally wiping out all the students enrolled in it. That kind of deletion anomaly can ruin a business instantly. So to fight these anomalies, the database enforces rigid constraints to maintain order. Domain constraints ensure a phone number field only gets numbers. Key integrity guarantees unique identifiers, and referential integrity mandates that foreign keys absolutely must match existing primary keys. It acts exactly like a tough bouncer at a club, checking IDs and tossing out any bad data trying to enter the system.
This discipline is definitely no accident. Edgar Cod baked this logical rigor right into his foundational 12 rules. Starting with Rule 1, all information in a relational database is represented logically in tables. Fun fact for you, IBM actually ignored Cod's paper at first because their older hierarchical databases were just making them way too much money. But ultimately, this mathematical elegance won out, making these the very systems trusted by banks and hospitals worldwide today.
And that brings us to Section 6, the Database Balancing Act. To wrap up this explainer, we need to objectively look at the reality of deploying these massive engines in the real world.
Look, while relational databases offer unmatched security, absolute data integrity, and immense scalability for thousands of users, they aren't exactly a silver bullet. The financial costs can be staggering. They require highly skilled administrators to manage their sheer complexity. And scaling them across global networks? That can actually bottleneck your performance, all because of those very same strict rules and constraints we just established.
Which leaves us with a fascinating question to ponder. As our global digital footprint continues to explode in size and unstructured variety, does the value of absolute mathematical order justify the escalating cost and complexity of the relational model? Will these strict rules continue to be worth the heavy overhead, or is the future of data going to demand something entirely different? It's an incredible balancing act, and definitely something to think about the next time you swipe your card.